In this episode, we're going to make two invisible network services feel very real and understandable because they quietly make modern computing possible. When you type a website name, join a coffee shop Wi-Fi network, or connect a new laptop at home, something has to assign your device a usable network identity and then help it find other systems by name. That is where Domain Name System, DNS, and Dynamic Host Configuration Protocol, DHCP, step in. People often talk about them like background plumbing, but if you understand the basics of how they work, a lot of security and troubleshooting suddenly makes sense. You do not need to memorize obscure settings for this. You just need a clear mental model of what each service is responsible for and how they cooperate to get you connected. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Start with a simple idea. Networks move information between numbered addresses, but humans prefer names. An Internet Protocol, IP, address is like a numeric street address that computers use to send packets to the right place, while a domain name is like a business name on a sign that people can remember and type. The job of DNS is to translate the human-friendly name into the numeric address so your device knows where to send traffic. The job of DHCP is to give your device its own network configuration so it can participate in conversations at all. If those sound like different problems, that's because they are, but they chain together in everyday life. You cannot reliably look up names if you do not have a valid address, and you cannot reach a server at an address if your device does not know how to route traffic. It helps to think of DHCP as the welcome desk for a network. When a device first joins a network, it usually does not know its own IP address. It does not know the default gateway to reach other networks, and it does not know which DNS server to ask for name lookups. If every device required a person to type those settings by hand, networks would be slow, error-prone, and frustrating. DHCP automates that setup by handing out a lease, which is essentially a time-limited agreement that says, for a while, you may use this IP address along with these related settings. The device gets a whole package of useful information, not just an address. That package commonly includes the subnet mask, the default gateway, and one or more DNS server addresses, which is a direct way these two services connect. Now picture what happens the moment you connect to Wi-Fi at home. Your laptop joins the wireless network and immediately needs to ask for configuration. It sends a message that is basically a broadcast shout, meaning it is heard by everyone on the local network segment, because the laptop does not yet know who the DHCP server is. The DHCP server responds with an offer, the laptop replies to accept, and the server confirms the lease. You can remember this as a short conversation that starts with discovery and ends with an agreement. The important beginner insight is that this exchange is local to the network segment, and it happens before you can comfortably do other network tasks. Without it, your device might assign itself a fallback address, but that usually limits connectivity and makes normal use unreliable. A lease exists for practical reasons that also have security implications. The network has a limited pool of addresses, so the server needs a way to reuse addresses after devices leave. If leases never expired, a network could run out of addresses even if most devices were no longer present. With leases, the server can reclaim addresses when the time ends, and devices can renew when they are still active. This also creates a record of which address was assigned to which device at a certain time, often tracked by a hardware identifier like a Media Access Control (MAC) address. That record matters when you are investigating suspicious activity and want to connect a network event to a specific device. For beginners, the key point is that DHCP is not just a convenience feature. It creates the foundation for identity on a local network. Once your device has an address and knows where the DNS server is, it can start using names. When you type a domain like a news site, your device needs to learn the IP address associated with that name. DNS works like a distributed directory, not a single central list. Your device usually talks to a local resolver first, often provided by your router, your employer, or your internet provider. That resolver may already know the answer because it has cached it, which is like keeping recently used phone numbers handy so you do not have to look them up again. If it does not know, it asks other DNS servers step by step, moving through a hierarchy until it finds the authoritative source for that domain. For beginners, the important idea is that DNS is built to scale and to avoid repeating work through caching. The DNS hierarchy can sound intimidating, but it is simpler when you think of it as levels of responsibility. At the top are root servers that know where to find the servers responsible for top-level domains like .com or .org. Those top-level domain servers then know where to find the authoritative servers for a specific domain. The authoritative servers hold the official answers for that domain, such as which IP address corresponds to a particular host name. Your local resolver acts like a librarian who knows which reference section to check, and it keeps notes so the next lookup is faster. The result is that your device gets a fast answer most of the time, even though the overall system spans the globe. That speed comes from caching, but caching has trade-offs that you should understand at a high level. Caching is why changes on the internet sometimes feel like they take time to spread. DNS records often include a timer that tells resolvers how long they are allowed to keep an answer before asking again. This time-to-live value helps balance performance and freshness. If the timer is long, lookups are faster and cheaper, but changes take longer to be noticed. If the timer is short, changes propagate quickly, but more queries must be made, and that can increase load. This also matters for security because attackers may try to trick resolvers into caching bad information, a concept sometimes discussed as poisoning. You do not need to know the exact techniques yet, but you should recognize that DNS is a high-value target because it sits at the moment where a trusted name becomes a destination address. If you control the translation, you can redirect traffic without changing what the user typed. Another common misconception is that DNS and web browsing are the same thing. They are connected, but they are different layers of the story. DNS is mostly about finding an address for a name, while web communication happens after that address is known. If DNS fails, you may see errors that look like you lost internet access, even if the network is otherwise working fine. If DHCP fails, you may have an address that does not belong on the network you joined, which also looks like the internet is broken. Beginners often blame the wrong thing because both problems can lead to the same symptom: nothing loads. A good mental habit is to separate the steps in your head. First, you get a local identity and directions from DHCP, then you translate names with DNS, and then you connect to services like web servers using other protocols. That separation makes troubleshooting and security reasoning much clearer. Let's walk through a simple, everyday scenario without getting tool-heavy. Imagine you open a laptop, join your home Wi-Fi, and type a website name. First, the laptop needs an IP address and network settings, so it uses DHCP to get them. Along with its own address, it learns the address of the default gateway, which is the device that forwards traffic outside the local network, and it learns which DNS servers to ask. Next, it asks the DNS server, "What is the IP address for this website name?" The DNS server answers, possibly from cache. Only after that translation does the laptop start a connection to the destination address. If any step is missing, later steps cannot succeed. This is why DHCP and DNS are so often at the center of connectivity issues, and also why attackers like to interfere with them. From a security perspective, both services are attractive targets because they influence where traffic goes and who gets access. If an attacker can run a rogue DHCP server on a network, they can hand out malicious configuration. For example, they could provide a default gateway that routes traffic through the attacker's device, or provide a DNS server controlled by the attacker. That would allow interception or redirection without the victim changing anything manually. In a beginner sense, this is a classic lesson in cybersecurity. The first systems you trust when you join a network have enormous power over your experience. Defensive designs try to limit who can respond to DHCP requests and try to ensure that DNS responses are trustworthy. You do not need to configure those defenses right now, but you should understand why the risk exists and what kind of harm it can create. DNS itself has its own set of security concerns because it is often unauthenticated at the most basic level. When your device asks for an address, it is trusting that the answer is correct. Attackers can try to exploit that trust by redirecting you to a fake site with a similar look, which can lead to credential theft or malware delivery. Even if the web traffic later uses encryption, a poisoned DNS response can still cause confusion, or it can steer you toward a destination that tries to get you to accept a bad certificate or share information willingly. Another angle is privacy. The names you look up can reveal what services you are using, even if your later traffic is encrypted. That is why modern networks sometimes use protective approaches for DNS queries. But the core concept remains the same. Name-to-address translation is a major control point. If you grasp that control point, you can better understand why so many security conversations come back to DNS. It is also worth noticing that DNS is not only for public websites. Networks use it internally to help devices find printers, file servers, and other local resources by name. In those internal cases, DNS records may be updated automatically when DHCP assigns addresses, which creates a convenient alignment between naming and addressing. That convenience is powerful, but it also means mistakes can create confusion quickly. If the wrong device is associated with a name, people may connect to the wrong system without realizing it. If old records stick around too long, a name might point to an address that has been reassigned to a different device. These are not just annoying issues. They can become security issues when a sensitive name resolves to an unintended destination. A beginner-friendly takeaway is that naming is a form of identity, and identity mistakes can have consequences. As you build your intuition, remember that networks operate at multiple layers, and DHCP and DNS sit very early in the sequence of events. DHCP is about getting your device onto the network with an address, a gateway, and supporting details, while DNS is about translating names so you can reach resources without memorizing numbers. Together, they make everyday computing feel effortless, which is exactly why they can be overlooked. The moment you treat them as foundational, a lot of security topics become easier to understand, like why segmentation matters, why attackers try to position themselves on local networks, and why defenders care about trusted infrastructure services. If you ever feel lost, come back to the story. A device joins a network, receives an identity and directions, translates a name, and then communicates with the destination.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.